Hi, this video will look at hypothesis testing for the mean when we have large samples. So first let's recall the decision rule based on p-value, where we use a p-value to make a conclusion on a hypothesis test comparing the p-value to the alpha level. And if p is less than or equal to a, we reject the null, and if it's greater than a, we fail to reject the null, implying that we accept the alternative. So recall that when sample size is greater than 30, that the sampling distribution for the sample mean is normal, and that means we would use the z-scores. The p-value for a hypothesis test is 0.0256. What is your decision if the significance is 0.05? Or what about the 0.01 level? So in the first case, 0.0256 is less than 0.05, so we would reject the null hypothesis. But in the second scenario, where we have a different alpha level, we would fail to reject the null because it's larger than that 0.01. So if we're going to use p-values to make a decision, we need to first find the p-value. And for a left-tailed test, or right-tailed or two-tailed test, we can do that. And we use the p-value based on our z distribution when we have large samples. So for example, in a right-tailed test, if we have z equal to 1.56, and if we look 1.56 up on our table, we'll see that it's a cumulative area of 0.940. So if we're finding the area to the right, we have to subtract that from 1. And 1 minus 0.940 is going to give us 0.0594. And that's our p-value. As another example, we might do a two-tailed test with a test statistic equal to negative 2.63. And so to find the p-value there, we've got to find the cumulative area on our z-table for negative 2.63, which we find to be 0.0043. The area to the left is 0.0043. And because it's symmetrical, we know that the area to the right is also going to be 0.0043. So if we multiply that by 2, we're going to come to 0.0086 as the total p area, the p-value. So this brings us to using p-values for a z-test. The z-test for the mean is a statistical test around the population mean. And it can be used when the population is normal and we know the standard deviation for the population, or for any population when the sample size n is at least 30. So the test statistic is the sample mean, x bar, and the standardized test statistic, because we're looking at large samples, is z. And z equals x bar minus mu divided by the standard deviation over the square root of n, which is our sample size. And recall that the standard deviation over the square root of n is also the standard error, and it's represented this way. So when n is greater than or equal to 30, the sample standard deviation s can be substituted for the population's standard deviation if it's unknown. So now we come to these specific steps, where first we state the claim mathematically and verbally, identifying the null and alternative hypotheses. We then specify a level of significance, alpha, and then we determine the standardized test statistic. That's the z-score. And we find the area that corresponds to that. And based on the area we find, we can then determine the p-value. For a left-tailed test, it's the area in the left. For a right-tailed test, it's the area in the right. And for a two-tailed test, it's 2 times the area in the tail of the test statistic. Next, we make a decision to reject or fail to reject the null, and then we interpret that decision in the context of the original claim. And here we go back to the example of the battery manufacturer. In this case, the manufacturer claims its batteries are good for an average of more than 1,000 charges. If we have a random sample of 100 batteries that have a mean life of 1,002 charges with a standard deviation of 14, our question is there enough evidence here to support the claim when we take alpha at 0.01, in other words, a 99% confidence interval? So the null is mu is less than or equal to 1,000, and the alternative mu is greater than 1,000. So the level of significance is 0.01. And our standardized test statistic can be found using the available information. And we've got our sample mean, our population mean is subtracted from that, and that's from the claim. We have our standard deviation, which is 14 from the population, and then our sample size of 100, and now that comes out to 1.43. Next, we look up 1.43 in our table, and we determine the area to the left of that and subtract that from 1. And when we do that, we come to 0.0764. P-value is greater than 0.01, fail to reject the null. So at the 1% level of significance, there's not enough evidence to support the claim that the rechargeable battery has an average life of at least 1,000 charges. That brings us to the concept of the rejection region and critical values. And the rejection region or critical region is part of the sampling distribution that includes the range of values for which the null hypothesis is not probable. That would be the area around P. If a test statistic falls in the region, the null is rejected because it's not probable to be there. So a critical value, Z, separates that region from the non-rejection region. So if we find the critical value and rejection region for a right-tailed test where alpha is 0.01, the rejection region is to the right of Z, which is 2.575. So to find the critical values in a normal distribution, we first specify the level of significance, alpha. We then decide whether the test is left, right, or two-tailed, and from there we find the critical values, Z. If the test hypothesis test is left-tailed, we find the z-score that corresponds to an area of alpha. If it's right-tailed, it's 1 minus alpha, and if it's two-tailed, it's 1 minus 1/2 alpha. So we then sketch the standard normal distribution, drawing a vertical line at each critical value and shading the rejection region. So the decision rule based on a rejection region, if we use a rejection region to conduct a hypothesis test, we calculate the standardized test statistic because that's our cutoff area. If the standardized test statistic is in the rejection region, then reject null. If it's not, we fail to reject the null. So if we're using a rejection region for a z-test for a mean, we first, this should be familiar, state the null and alternative hypotheses, specify our significance level, sketch the distribution, determine the critical values using our z-table, and determine the rejection region. We then calculate our standardized test statistic, and then make a decision to reject or fail to reject the null. Again, if z is in the rejection region, we reject the null, otherwise fail to reject. And finally, all this needs to be reinterpreted into the original claim. So returning to our example of the telephone company that claims the average phone call is 8 minutes, if we have a random sample of 58 calls with a sample mean of 7.8 minutes, and a standard deviation was 0.5 minutes, is there enough evidence to support the claim that at the alpha 0.05 level? So the level of significance down here is alpha set to 0.05. The claim is mu will equal 8. That's the alternative, is that it will not. Here we have our test statistic being calculated by subtracting the population mean, which is from the claim, from the sample. Our 58 phone calls gave us an average of 7.8, and then over the standard deviation of the claim, 0.5, divided by the sample size of 58, and what we find is negative 3.05, and that test statistic falls in the rejection region. So the null, which is mu equals 8, is rejected. So at the 5% level of significance, there is enough evidence to reject the claim that the average length of a phone call is 8 minutes.